open loop gain as a function of frequency. How gain depends on the frequency of input source. Okay, so put that in open loop gain as a function of frequency. Okay, so because of this dependence, we can design op-amp, okay, which can act as a low pass and high pass filters. So we know that our op-amp, this is my op-amp, okay, this plus, this is minus. So whenever I apply a difference of voltage here, okay, you know that op-amp can be approximated by this voltage gain AB, AVID. I'll get the gain. Okay, here I have a output resistance R0, R0. Okay, and here I'm getting V0. Suppose I put a capacitor here. Okay. Now, what will the value of output? Say capacitance C. Okay, and when capacitance C is reactance, we know XC is given by 1 upon J omega C, isn't it? Okay. Now I want to find what is this voltage across this capacitor, because this is only our V output. So I can use this loop. Okay, I'm applying some VID. I'm getting some voltage here. Okay, if this R0 is 0, then almost all voltage coming here and it is across here. But now R0 is there, so there will be division of voltage, isn't it? If R0 is 0, there's a whole voltage across this one is equal to capacitor voltage. Okay, but this R0 is there will be division of voltage. So I can write the expression for V0 as, okay, I want capacitor XC upon total resistance is R0 plus XC. Okay, and into I can get this is, say this is my source now, E VID. Okay, so this is my expression for now, expression for voltage. Okay, and you can put the value of XC now. So if I put the value of XC, what I'll get? I'll get 1 upon J omega C R0 plus 1 upon J omega C. Okay, and I have this VID as it is. Okay, let us simplify it a little bit more. Okay, so if I take this LCM, this will cancel out J omega C. So I will be left with a VID upon what, 1 plus J omega C R0. Okay, now let me further write omega as a omega is angular frequency of source, input source. Okay, let me write like as a J 2 pi F, J is there, 2 pi F, okay, C R0. Okay, and let me define a cutoff frequency, say FC, which is a cutoff frequency. The meaning will be clear now. What is cutoff frequency? Okay, equals to 1 by 2 pi C R0 0. Okay, so once I write FC value, now this expression will become a VID, okay, upon this become 1 plus J F upon FC, isn't it? Okay, and now you can see from this expression, okay, now your output depends on frequency. Okay, so if frequency increases, this expression, total expression decreases. Okay, so if I write now the V output, okay, now V output upon V input, okay, which will be difference. So I call it open loop gain as a frequency, which is nothing equals to V0 upon VID. Okay, and that is equals to A upon 1 plus J F upon FC. Okay. Now this gain depends on frequency. As frequency increases, okay, your gain decreases. So what is AOL? Okay, AOL is open loop gain as a function of frequency. Okay, and what is your A? A is also gain. Okay, so your A is what? Your A is simply, I can call it, when there is a, this is a frequency independent, okay, at zero frequency. Okay, open loop gain is the open loop gain. This is open loop gain A, open loop gain, okay, at F is equal to 0 hertz, that is zero frequency. Okay, okay, at out open loop gain at zero frequency. Okay, and FC already have defined. F is the operating frequency. F is the operating frequency of input, and FC already were defined. FC is your cutoff frequency. Okay. Cutoff frequency. Okay. So up to this is clear. Okay. हाँ.
सर इसमें J क्या है?
J is iota. J is your iota. Okay.
Okay.
Now.
सर cutoff frequency क्या मतलब इसका क्या?
हाँ बता रहे हैं ना, कटऑफ बता रहे हैं कटऑफ फ्रीक्वेंसी क्या है. ओके, सो नाउ सपोज I have already got this AOL. Okay, AOL W is A upon 1 plus J F upon FC. Okay, if I want to take magnitude of this one AOL W, इसका magnitude लेना है तो magnitude क्या आएगा? A upon 1 plus, okay, this is a complex number x plus iota y. Okay, a plus iota y और jy, तो मैग्नीट्यूड क्या होता है? एक्स स्क्वायर प्लस वाई स्क्वायर. ओके, तो इसका मैग्नीट्यूड क्या हो जाएगा? एफ अपॉन एफ सी का स्क्वायर. ओके, दिस इज कॉम्प्लेक्स नंबर. इफ आई टेक मैग्नीट्यूड ऑफ होल तो ये आएगा मैग्नीट्यूड. ओके, नाउ इसको लिख लो पहले, f by fc. Okay, now I say if f equal to fc, if I put f equal to fc, okay, then what will become if I write f equal to fc? So already this should be clear. Frequency increasing, gain is decreasing. Okay, so if I put f equal to fc, then my open loop gain, okay, okay, at f is equal to fc, fc is equal to what? A upon root 2. Okay, so this is the definition of frequency. Or root 2 means क्या? 0.707 okay, so frequency at which the gain, okay, the gain of the circuit or open loop gain is A by root 2. Okay, where you know A, where A is gain at zero frequency. Okay, तो zero frequency पे जो gain है that will decreasing. So at cutoff frequency is the frequency at which the gain becomes 0.707. Okay, now here we have output. Okay, open loop gain. Okay, now this is a complex quantity, so it should have a phase. That means your output should also have a phase. Okay, so if I want to write the phase of this output, okay, what is the phase of this output? Okay, so this is the phase. Write the phase of this output. So if I want to write the phase, okay, let me write this function as a v naught a vid 1 plus j okay, f upon f naught. Okay, now I want to write the phase of this one. Okay, तो phase कैसे लिखते हैं? Okay, just write multiply by j f upon f naught 1 minus j f upon f naught. Okay, let me write in the form where I can write the where I can write complex number. Okay, so this will become what? Solve this one. What will become? Tell me. If I solve this one, what will become this one? A. Okay, this will become what? F plus jj square f upon f naught square. ये ठीक है क्या? This one minus j this plus cancel and this is plus minus j square f upon f naught square. Okay, upon a vid minus j f upon f v naught upon 1 plus f upon f naught square.
सर प्लस की जगह माइनस होगा
कहाँ पे?
डिनोमिनेटर
माइनस क्यों होगा भाई? प्लस माइनस माइनस जे स्क्वायर माइनस में नहीं आएगा, आइटा स्क्वायर माइनस में नहीं आएगा.
ठीक
Okay.
है सर.
Now if you want to write the phase of this output, okay, so you know what is the phase? For phase of any
सर सेकंड टर्म के साथ AVID आएगा.
हाँ VID आएगा, AVID तो दोनों कॉमन ही है. Okay, now you know if a number complex number is x plus iota y, okay, its phase is given by what? Tan inverse
y by x.
y by x. Okay, so यहाँ पे phase क्या आ जाएगा बताओ मुझे? phase क्या?
fc.
Okay, only tan inverse f upon मैंने f नॉट लिख दिया, आप fc लिखो जो भी है, fc और f नॉट जो भी है. ओके, fc तो tan इनवर्स f upon fc माइनस माइनस भी है यहाँ पर. ओके, so this is your phase of output. Now phase is also, you can see. Now let me first talk about the gain. Okay, so gain is also changing with frequency and phase of the output also changing with frequency. Okay, now just now I told you that gain decreases with frequency. Okay, suppose this is my gain. Okay, and this is my frequency axis. Okay, so my gain decreasing with frequency. Okay, and the point here fc is the point. Okay, fc is the point where this is fc is the point where your a open loop gain, okay, is equals to a upon root 2, where a is the, okay, or 0.707 a. Okay, and because particularly this particular circuit is a low pass filter, so high pass filter, as frequency increasing, my open loop gain is decreasing. At infinite frequency it becomes 0. Okay, so this is my gain is changing with frequency. Okay, similarly if I say my frequency, okay, if I say frequency at 0, so it will be 0, and if it become infinite, then it become minus 90. Okay, if it is an infinite, tan infinite is 90. Okay, so if I say this is 90 degree, and if I say this is phi, and this phi is also function of f, if I say it phi at 0, frequency is 0, and so it also changes, and at infinite becomes minus 90. This particular circuit. Okay, frequency also varying with as a function of, okay, frequency. So this particular circuit you can see it won't work for high frequency. High frequency for gain will decrease. Okay, so this is for example for low pass filter. Okay, so this only low pass, low frequency it will allow, and all other frequency will decay, but they decay very fast. Now generally whenever we write this gain, okay, gain we write in terms of decibel. So let me write now this equation in the form of gain as a decibel. So I know my a open loop gain as a function is equal to a upon 1 plus j f upon fc. Okay, now if I write gain in dB, decibel, okay, that will be equals to what? 20 log 10 AOL. Okay. Now this what I can write. I can put this value here. This will give me 10 log 10 A. A is the gain at zero frequency minus 20 log 10. Okay. 1 plus J F upon FC. Or let me take the magnitude of this one. Okay. So AOL. Okay. So AOL magnitude will be A upon 1 plus F upon FC square. Okay. So say this is F upon square. And this is for gain. This is also magnitude. Now let us understand how गेन जो है फ्रीक्वेंसी से कैसे डिक्रीज होता है। फॉर एक पर्टिकुलर एग्जांपल ले लेते हैं। फॉर एग्जांपल कोई पर्टिकुलर सर्किट है, इसके लिए एफसी इज योर 5 हर्ट्ज। ओके, एंड उसका जो जीरो पे गेन है, जीरो फ्रीक्वेंसी गेन इज गिवन बाय 2 × 10⁵ ओके, अब हम क्या फ्रीक्वेंसी को चेंज करेंगे एंड देखेंगे कि गेन कैसे डिक्रीज कर रहा है। Okay, so this is now my formula. Okay, decibel in dB. I'm going to use this formula. इसी formula में I'll put different frequency and I'll see how gain changes. Now suppose if I take FC equal to 5 hertz, okay, and A this one, okay. Now let's say when my F is 0, when F is 0, this F is 0, what is my gain, which is equal should be A. So AOL, okay, at F is equal to 0 in dB, what will the value? Okay, 20 log 10, A value already this one, 2 × 10⁵. Okay, this will become, you put F 0, this should become 0. log 1 क्या होता है? log 1 क्या होता है 10 में? 0 होता है कि होता है 0? This becomes 0. Okay, now what is the value of this one? Okay, so you take log 10 5, so this become 100 log 10 upon 10 plus 20 log 10 2. Okay, so this become your 100 and log 2 values 0.3, so this is, it will come almost 6. Okay, approximately, so I'm writing approximately, this is the value is now 106. Okay, 106 dB. That's zero frequency, the open loop gain. Okay, if I convert this one for this particular circuit, this is almost close to 106 dB. That means this conversion of this one in dB, इसको dB में कन्वर्ट करेंगे तो 106 आएगा. Now secondly you put now next, okay, let F equal to FC, that is 5 hertz. Okay, and again put the value here, so your gain at F equal to FC in dB become what? This is same 20 log 10, ये तो चेंज होगा नहीं, माइनस ये, ओके, माइनस 20 log √2 आ जाएगा, isn't it? और इसको सॉल्व करो आप, इसको सॉल्व करने में कितना आएगा बताओ, कितना वैल्यू आना चाहिए? So this is your 106, okay, and this is almost how much? Log √2.
सर
थ्री,
रूट क्यों आया है?
यहाँ पे रूट नहीं था क्या हमारे पास में? गेन में जो नीचे फॉर्मूला था, हमारा फॉर्मूला था ए नॉट डब्ल्यू का फॉर्मूला था, उसमें गेन यहाँ पे रूट था ना?
यस सर।
गेन में जो था, प्लीज करेक्ट दिस वन. ओके,
3.0.
okay, so it's almost 3 will come. So I say now this is 13 dB. Okay, so here you can also define the again definition of cutoff frequency. Okay, the frequency, okay, cutoff frequency is what? Cutoff frequency, okay, f equal to fc, okay, at which gain decreases by 3 dB. Okay, the frequency at which gain decreases by 3 dB is called your cutoff frequency. So earlier it was 106, now it becomes 103 dB. So this is your cutoff frequency definition. Okay, now what I'll do, I will keep on multiplying this by a multiple of 10. Now it's 5 hertz. I'll use it for 50 hertz, 500 hertz, and I'll see how my gain changes. Okay, so the next is, third point is, you are just put here f equals to, now third is 50 hertz. Okay, and you need to solve for 50 hertz and tell me what is the what you're getting. AOL, okay, at f equal to 50 hertz, what you're getting. So this will be same. Okay, 106 minus this, how much will become? If 50 hertz, this is 5 hertz, this is 5 hertz, is 50, 10, 100. Okay, so is 20 log 10 under root, how much? 101. How much will come? So basically what will come, if I put here 2, 10, okay, 20, so it will almost come, this will also almost be log 100 is what? Log 100, this is, suppose this is 100, so it become 10, this become again 20, this is 20, so almost it will come 86 dB. log 100 10 हो जाएगा ना, 10 log 1 हो जाएगा, and 20 log 1 हो जाएगा, 20 so 20, so 26. Okay, similarly if I next I do f equals to 500 hertz, okay, and then my gain at 500 hertz will become 106 minus 20 log how much? 1 plus 100, huh? 1 plus f upon fc, how much?
10,000.
Okay, 10,000. 10,000. So how much? 10,000 means what? 10 power 4. Okay, so how much?
106 minus 80.
Just check it. Okay, so we've done
40 over.
106 minus 40. How much is coming?
66.
66 dB, right? 66 dB. Okay. Similarly, now you do one more time. Now we are getting close to that one. Okay. Now fifth, you take let f equals to 5 kilohertz. Okay, 5,000 hertz. Then your AOL at f equal to 5 kilohertz will become 106. Okay, so what will come if you solve, keep on solving this one, it will come almost 46 dB. 46 dB. Okay, so if you increase frequency by a decade, your gain is decreasing by 20 dB. Okay, and if you go for 50, okay, if you do it 50, 650, 50 kilohertz, f equal to 50 kilohertz, you can check 50 kilohertz. Okay, your AOLW, okay, will become almost 26 dB. Okay, and that's way it will be keep on decreasing. Okay, and now I'm not multiplying by kilohertz. I'm just writing a somewhat higher frequency, say 1 megahertz. Okay, and at this frequency your open loop gain, okay, that will almost become 0. So why I'm doing like this? Okay, why I'm talking about 20 dB? Okay, so you see the gain is constantly decreasing as I'm increasing by 10 frequency multiple of 10. Okay, my gain is constantly decreasing. Okay, so now let me draw this, the variation of frequency, variation of gain with the frequency. So if I now because I'm writing gain as a in decibels, okay, in dB, okay, so the graph will be very smooth. Okay, so what will happen, this will be almost constant. Okay, so suppose this is 106. Now if I come to cutoff frequency f equal to fc. Okay, the loss, that the decrease is very less. Okay, here you have 103 dB, and after that if you keep on increasing frequency, okay, it's okay. So this is the slope of this graph is minus 20 dB per decade of increase of frequency. Okay, at a higher frequency it becomes 0. So because you're putting log now, so the graph would look like a straight line with negative slope. Okay, so this is the first order circuit. So first order circuit, whenever you have one capacitor, the gain decays by minus 20 dB per decade. And I already defined cutoff frequency is the frequency at which your gain is reduced to 3 dB, only 3 dB. So what we can assume here, what I'm trying to say here, that you can say that your gain is almost contained up to this frequency. Okay, after this frequency, this particular circuit, this all frequency becomes gain decreases. Okay, that means you can say this circuit is acting as a low pass filter. It is allowing the frequency to propagate. Okay, or it's allowing the frequency without loss up to cutoff frequency. That's why cutoff frequency is important. Okay, so iske niche ki the frequency below this one, they will go without loss of gain. Okay, while if you put very high frequency, you won't get any gain. So so high frequency gain is 0 and low frequency gain is constant. That's why it is a low pass filter. Okay, so this is a particular low pass filter. Now there can be circuit which can apply high, they can only allow high frequencies. Okay, there may be circuit which can allow all the frequencies, that is all pass filter. There are those filters which can only apply a particular band between two cutoff frequencies. Okay, that is called, there will be band pass filter. Now all these 4 type of filters we have to understand using this operational amplifier. And particularly here, this is minus 20 dB decade. This is not necessary. Okay, there, if you want to increase, there can be circuit where it can be minus 40 dB per decade, depending on a circuit. Okay, depending on a circuit. Here we have only one capacitor, so and this can be minus 60 dB per decade. Okay, what is the order of the filter? What is the first order, second or third order? So that decays can be faster decay. So better the decay faster, that is the better, that filter will be better. Okay, that will high frequency, that will be decay really fast, so that will only apply low frequency, otherwise the slowly decrease. Okay, with low frequency you got some high frequency mixing also. Okay, so this is your open loop gain as a function of frequency. Now we will take filters one by one. Okay, up to here is clear? Any confusion up to here? Okay, now let me talk different type of filters. Okay, so first is your low pass filter. Okay, low pass filter is the filter which just now we have seen. Okay, so this is your gain, or output is a frequency. Okay, and this is your low pass filter. Okay, it allows frequency up to fc, and this get decays. Okay, so this is a low pass filter. Similarly, if I say which is my high pass filter, so second is your high pass filter. High pass filter will allow high frequencies only, and at low frequencies the gain will decrease. So that will be like this. The plot will be for, okay, open loop gain is a frequency, it's a function frequency. Okay, so up to here they will decay very fast, but above cutoff frequency the gain is constant. Okay, so this is a high pass filter. Similarly, you have pass band filter. Pass band filter means they will only allow a particular band of frequency to go without loss, constant. All thing will be, or other things all will be decay. Okay, so let me this one. Okay, so these kind of it will be having two frequency, so cutoff, lower cutoff frequency and higher cutoff frequency. Okay, FC1, FC2. Okay, so in this frequency range you have a almost constant gain. Okay, almost constant, you can make almost constant gain. But if your frequency is lower than this one and if you're higher than one, then gain is reduces very fast. Okay, so this is your pass band filter. This will allow any band. So similarly, there are all pass filters. There is also a stop band filter. Okay, stop band filter means it will stop a band and it will allow everything else. Okay, so next is your stop band filter. Okay, stop band will give you the frequency constant. Okay, except some band. Okay, so this is your A gain. You're applying frequency here. Okay, so at between two frequencies, gain is very fast, gain is very low. Okay, gain is very low, but below this frequency and above this frequency you get constant gain. Okay, that is why this is called stop band filter. It is stopping this band. Okay, it is allowing this band. Okay, this is high pass filter and that was your low pass filter. So these are different type of filter, and we have to show some circuits open. Okay, how they perform this filter and filtration operation or filtration function. Now put the adding first order low pass filter. First order low pass filter. First order low pass filter. Okay, so low pass filter we already done, but I am doing now a little bit different way. Okay, so you have, say this is your R1, you say this is your RF or R2. Okay, so this is your R1, this is your RF, and here you have your output. Okay, here I am putting one capacitor here. Okay, I am putting one resistance here. Okay, say R2, and here I am applying V input plus -1, and let us say this is grounded. Now without solving you can check whether this circuit is a low pass filter or high pass filter. Okay, so this is the input. Okay, this is sinusoidal. This is sinusoidal. That means this is a frequency dependent input. Okay, it is square wave. It may be no, not square square wave with frequency. Okay, it can be your sinusoidal wave. Okay, so AC source. Basically, this is AC source with a frequency. Now, and say this is my capacitor C. Now, suppose this is a high frequency. So high frequency, what is it? So how capacitor reacts for high frequency, low frequency? If the frequency is low, then your capacitor is what? For low frequency DC, capacitor is what? Open. Okay. When I say low frequency means I am talking about what? I'm talking about the DC. So if the frequency is low, then what will this become open? Okay, and you get some voltage here, and you let the voltage get amplified as a non-inverting amplifier. This is a non-inverting amplifier. And suppose the frequency is high, then this circuit will become what? This capacitor will become short. Okay, so you know, for low frequency or DC, okay, capacitor acts as open circuit. Okay, and for high frequency, okay, capacitor, okay, behaves like short circuit. Open circuit means high resistance. Short circuit means because the XC of the capacitor is 1 upon J omega C. If frequency is high, then XC becomes 0. Okay, if omega is high, infinite, XC becomes 0. That means behave like a short circuit. Okay, if omega is 0, XC becomes infinite. That's why it's become open. This is open, and this is short circuit. Okay, now if I apply this concept on this particular circuit, so if it high frequency, this becomes short circuit. So this the voltage of here becomes 0. So if you input voltage itself is 0 here, then gain will be also 0, because the gain is what? If I say here voltage is V plus, if it is V plus becomes 0, then obviously your V output becomes 0, because V output is nothing. V output is what? V output is your 1 plus RF upon R1 V plus, isn't it? That becomes 0. That means it's not allowing high frequency. High frequency gain is 0. That means it's a low pass filter. Okay, like that you can check without solving the function whether it is low pass filter or high pass filter. Okay, now we'll calculate the expression for V0. Okay, and we'll see again. We can see that is a low pass filter. Okay. Now, what is the value for V plus? Just put the V plus value, you will be output. What is V plus? Okay, V plus again across this capacitor. Okay, and total voltage this one, and the resistance total impedance is this R2 plus XC. Okay, so 1 plus R2 plus XC, okay, into XC into your V input, that is your V plus. Okay, and XC is what? XC is your 1 upon J omega C. R2 is R2 is again 1 plus J omega C into V input. If you solve this further, this become cancel out. So like previous example, you get J omega C R2 V input. Okay, this is V plus. So your gain will become V0 upon 1 plus RF upon R1. Okay, 1 plus J omega C R2 V input. Okay, and the gain become V0 upon V input. Okay, 1 plus RF upon R1, and this I can write, okay, Again, what I can write? J F upon FC. Okay. I can write this is 2 pi. 2 pi. Oh, let me write. Okay. Here 1 plus J 2 pi FC R2. Omega is 2 pi F. So open loop gain becomes 1 plus RF upon R1, 1 plus J F upon FC. Okay. Magnitude of gain again 1 plus RF upon R1. Okay. Under root 1 plus F upon FC. And if you get phi will tend, what will the phase? For this particular question, what is your FC? FC is nothing. FC is your 1 upon 2 pi C R2. This resistance. Okay. Now, if I put, if omega is infinite, okay, or F is infinite, then gain is 0. Then gain is 0. If omega is 0 or F is 0, okay, 0, then what? Gain is what? Constant. It has become 0. The gain become almost constant. What is the gain value if it is 0?
1 plus RF over R1.
Yes. So gain will be what? Gain will be 1 plus RF upon R1. This is your gain of the circuit. Okay. So low frequency, zero frequency, similarly up to FC will get almost constant. After that will decrease. Okay. So you can now plot the graph. So if you go like this, so initially it is constant, then it decreases. Okay. Yeah. To FC it is constant, and that has become 0. Okay. So this particular circuit is example of low pass filter. Low pass filter. Okay. Phi expression for phi will be same. We will calculate what is minus tan inverse F upon FC. In particular, this example, you can check. Okay. Now let us do high pass filter. First order high pass filter. तो इसके एग्जाम में बहुत से प्रॉब्लम आती हैं. Okay, I'll give you some around. We'll solve some 10 problems, different type of filters on this topic. This is a very important topic. इसमें से हमेशा क्वेश्चंस आते हैं. Now high pass filter. Okay, so what is high pass filter? Same circuit, only replace the position of. This is only 2 example of high pass filter. There will be many circuits. Okay, एग्जाम में बहुत से सर्किट देगा, आपको पहचानना पड़ेगा कि यू हैव टू आइडेंटिफाई व्हाट इज द लो पास फिल्टर ऑफ और हाई पास फिल्टर. ओके, सो से दिस इज योर R1, say this is your RF, this is your V0. Okay, here this time I'm putting here resistance. Okay, say R2 I'm putting here. Okay, I'm putting capacitor here. and I'm giving here your V input same, like only I have replaced the position of this one. Okay, position of this capacitor. Everything else is same. Now please solve again, same procedure. Give me the expression for gain.
सर
Hmm.
लास्ट क्वेश्चन में जो गेन
Yes. Can you repeat?
इन्वर्टिंग एम्पलीफायर
This is non-inverting ना? Last question में तो inverting ही था.
तो सर
गेन का क्या?
गेन का फॉर्मूला 1 + RF/R1 लिखे थे.
हाँ, यस. भाई वो तो नॉन इन्वर्टिंग था, तो गेन का फॉर्मूला तो 1 + RF/R1 ही होगा ना.
सर दिस इज नॉन इन्वर्टिंग.
दिस इज नॉन इन्वर्टिंग ना. यू आर अप्लाइंग प्लस, इनपुट इट इज प्लस ना. लास्ट क्वेश्चन में मैंने साइन चेंज किया था क्या?
नहीं सही था सर.
ठीक है ना.
ओके सर.
सर ये हाई फ्रीक्वेंसी अगर होगी तो जब ये शॉर्ट होगा तो वी इनपुट ही आ जाएगी V प्लस पे.
अभी देखो, ये अगर लो फ्रीक्वेंसी है तो ये ओपन हो जाएगा.
यस सर.
ओपन हो जाएगा, या कुछ वोल्टेज आएगा ही नहीं.
नहीं सर, हाई फ्रीक्वेंसी के लिए V इनपुट.
तो हाई फ्रीक्वेंसी के लिए तो या करंट आएगा ना.
यस सर.
तो इसका मतलब हाई पास फिल्टर है.
ओके.
if you apply low pass, if you low frequency, this become open. Okay,
यस सर.
ओपन आ गया तो यहाँ ये डिस्कनेक्टेड हो गया सर्किट से, यहाँ पे जीरो आ गया, तो जीरो विल नॉट गिव यू जीरो आउटपुट. ओके,
Yes.
so that's why it is a high pass filter. Okay, find again your V naught is what? V naught is again 1 + RF upon R1 V plus. This time V plus is changed. This time your V plus will be simply across R2. Now V plus is across R2. Okay, R2
in
okay, so this is R2 plus
XC
into your V input. Okay, so R2, okay, R2 plus 1 upon J omega C, okay, into V input. That will become R2 J omega C V input upon 1 + J omega C R2. Okay, put this value here. So you get V output equals to 1 + RF upon R1. Okay, then you have R2 J omega C V input upon 1 + J omega C R2. और इसको रहने दो अभी इसको ऐसे रहने दो. इसको यहीं पे चेंज कर सकता हूँ क्या? I can change this is here itself. Okay, then होगा क्या सही? चलो जो भी आ रहा लिखो. फाइनल बताओ क्या आ रहा है मुझे पास. How can I write this one? Or I can change here itself. Okay, इसकी जरूरत नहीं पड़ेगी लिखने की. So you can write, okay, this you can write a simple form. You can here itself you can modify. You have R2 J. Okay, so your J you can write 2F phi SC. Okay, 2 pi FC into V input. Okay, now tell me the final answer. What is coming? Solve it. I want to see what is coming.
1 + RF/R1
Hmm.
multiplied by JR2 F/FC.
ऊपर भी आ रहा है. Okay, so better I want J here. No, you multiply J here. Okay, so this will become what? It will become R2. Okay, R2 multiply by J. This become minus J, isn't it? Into V input. Okay, and this is 1/2 this 1/2 F. Okay, 2 pi R2 is not R2. I will take common. Okay, so take R2 also common. So this R2 will cancel. Okay, so this R2 will come here. and this R2 will cancel. This is the correct way to do. Okay, now this become, okay, now I put j multiplied by j, so this becomes j, okay, j upon 2 pi f c R2. Okay, this is good. Okay, now if I want to write further, my v plus will be this R2 cancelled, so this will be simply v input 1 minus j, okay, and this is 2 pi f, so I can write omega c upon omega, okay, or I can write v input equals to 1 minus j fc upon f. This time your f is coming at bottom because this high pass filter, low pass filter, f was coming here. Okay, this is v plus, and now you can write v output is equal to 1 plus rf upon r1, okay, into this one v input upon 1 minus j fc upon f. Okay, this is your formula, and here you can write the formula for gain function of frequency will be 1 plus rf upon r1, okay, 1 minus j fc upon f. Okay, now if f is 0, okay, this become f is 0, this become infinite, and gain becomes 0. Okay, if f is infinite, okay, so this becomes 0 and gain becomes constant, 1 plus rf upon r1. Okay, so this is a high pass filter. Similarly, you tell me what is the formula for now this phase difference for this particular case. How much phase difference is coming? From here, you tell me what is the formula for phase difference. It should come same. उल्टा हो जाएगा बस. Earlier it was f by f. और minus sign आ रहा है क्या? Sign, please sign, check sign also. Okay. So now this time your phi will be 10 inverse. It will multiply this by 1 minus j. Okay. It will multiply this one.
प्लस में आएगा.
प्लस में आ रहा है, प्लस में. So this time your प्लस में आ जाएगा. माइनस से प्लस से मल्टीप्लाई करेंगे, ठीक है. हाँ, तो प्लस से करेंगे तो प्लस आ जाएगा. तो दिस विल बी गेन विल बी नाउ fc upon f. This will be your f. Okay. So complex number, how to calculate the calculate the phase for a complex number. Okay, that you have to revise. Okay, tomorrow we will do problems. There you will be requiring how to calculate the phase. So if your number is complex number is given, you know how to do phase. Okay, so that just revise again before coming to the class. Tomorrow we will do some more problems. So I'm stopping here. We'll start digital electronics class now.
Okay.
Okay. Thank you.
Thank you, sir.
सर.